Let's look at optimization. So just a reminder of how you find absolute max or min on a closed interval is first you make sure your function is continuous on that interval, find the critical points within the interval, then evaluate the endpoints and the critical points. The largest is the max and the smallest is the min. The second derivative test tells you the concavity. So if the second derivative at a point is positive, then it's concave up, which would mean it'd be a minimum. If it's negative, then it's concave down, it would be a maximum. And so this is a nice way to just find the critical point, the first derivative, so you know at the critical point your slope is 0, so there's going to be a max or a min or neither. And then I evaluate the second derivative, and that gives me my information that I'm looking for of my minimum or my maximum. Let's look at an application of maximizing revenue. So the regular airfare from Boston to San Francisco is $500. An airline using planes with a capacity, so the most they can get on the plane is 300 passengers, they observe that they are only averaging about 180 passengers. So as you can see, they're below capacity. Market research tells the airlines managers that each $5 fare reduction, so if they reduce the fare by $5, would attract on average 3 more passengers for each flight. How should they set the fare to maximize their revenue? So R of n, let that equal revenue, where n is the number of times the fare is reduced, because that's what they're looking at. How many times should they reduce the fare? So the regular airfare between Boston and San Francisco, $500. That's important. And then minus, so my price is going to be $5 times how many price reductions. So if there was 1 price reduction, 2 price reduction, and all that good stuff. Because remember, we find revenue by quantity times price. So the quantity would be the number of passengers plus 3 more passengers for every time we have this price reduction. So if I go back to my price, 500 minus 5n, my quantity, 180 plus 3n, that's how I come up with my revenue. Remember, revenue is price times quantity. But typically, we've just been doing X times P, right? But in this case, we have actual equations for the price and for the quantity. So I just simply FOIL this all out, 500 times 180, 500 times 3n, 5n times 180, 5n times 3n. And then I collect my like terms, the n terms, and I can see that my domain's going to be from 0 to 40. Now, where in the world did I get 40? If you think about it, if you're adding 3 more customers for every $5 reduced, if I only have the capacity of 300 and I'm already saying 180s on there, well, if I do this 40 times 3 is 120. 120 plus that 180 gives me my 300. So this is my domain. This says this is the only how many number of times I can reduce, because otherwise, if I just keep reducing, I have went over my capacity. So I can't do that. Okay, remember what we're doing. We're maximizing revenue, and this was our revenue function. So how do we find the max? We take the derivative. So the derivative, 600, 2 times 15, 30. We set it equal to 0, and then we solve this for n, which would give us our number of price reductions that would maximize revenue. I factored out a 30, so it makes it easy to see that this piece right here, when it equals 0, would be when n equals 20. So that's my critical point. So the question is this a max or a min? Well, what you could do, you plug your critical point into the second derivative. Notice when I take the second derivative, actually my variable goes away, but it's negative. When it's negative, that means I do have a max. So I evaluate with my revenue function, my endpoints, and my critical points. Remember, my endpoints was 0 to 40, my critical point. And I look and I see my critical point 20 is the largest. So I can see that the best fare to maximize the revenue is my revenue 500, my price here, 500 minus 5 times 20 equals $400, with 180 plus 3 times my critical point, 240 passengers. So we still don't get it to capacity, and it might, the only way you can get it to capacity is reduce it even more. Instead of $5, maybe $10. But then this gives me my revenue. And so I can see here that the number of times the fare is reduced is my x-axis, so 20 gives me my max of my revenue function. Let's look at another example where an office supply company sells X permanent markers per year at a $P price per marker. The price demand equation is given 10 minus 0.001x. What price should the company charge for the markers to maximize the revenue, and what is the maximum revenue? Well, how do you find revenue? Remember, it's X times P, the quantity times the price. Well, we're given a price function times the quantity, which is X, so I get my revenue function. My domain is certainly we want to sell more than 0 markers, okay, and we don't want it negative, so it needs to be greater than or equal to 0. My price, I want greater than or equal to 0. So what I do is I solve this inequality by, I could throw this negative 0.001x to the other side. I divide both sides, 10 divided by 0.001, so I get 10,000, which says I have to keep the number of markers between 0 to 10,000. What price should the company charge for the markers to maximize the revenue? Well, let's find the critical points. Here's my revenue. I take the derivative. I set the derivative equal to 0. I solve for X, and I get my critical point that I want to know if it's a max or a min. How do I know if it's a max or a min? Just like the last example, we take the critical point and we plug in to our second derivative. Well, when we take the second derivative and the variable goes away, there's nothing to plug in, but if you kind of notice, my x squared this is negative, so it's going to be upside down, meaning it's going to be a max. And then finally, I plug in the endpoints, which were 0 and 10,000. I plug in my critical point, and I see which one of these is the largest. That gives me my maximum revenue. Well, it said, what price should the company charge for the markers? Well, I had a price equation. So I take my critical point of 5,000, and it says the company should charge $5, and then I plug that into my revenue, which give me my 25,000, and so the company will realize a maximum revenue of 25,000 when the price of the marker is $5. So now they've come back and they have given us a cost function. So the annual cost of manufacturing our markers is given. What is the company's maximum profit, and what should they charge for each marker, and how many markers should be produced? Well, remember how to find profit? Revenue minus cost. Well, we just found our revenue function. They've given us our cost. So I simply plug in my revenue minus my cost. Please don't forget to distribute that negative sign. And now I collect some like terms. And my profit domain is going to be the same as my revenue so this still remains the same. How do I find, now that I have a profit function that I want to maximize? I find the critical points, meaning I find the first derivative. I set the first derivative equal to 0. So you can see you're just doing the same thing over and over and over. How do you maximize or minimize? Find the function that you want to maximize or minimize, take the derivative of it, set it equal to 0, solve it for x. So I've solved this for x. I have a critical point. I know that this is a max because my second derivative is negative. And so now I can look at my endpoints of 0 and 10,000. I can look at my critical point of 4,000 and see that's where my absolute max is, which says a maximum profit of this 11,000 is realized when my critical point, 4,000 markers, are manufactured, and I plug that into my price equation and sold for $6 each. And I can look at the graph. This is kind of interesting to look at the graph of all of these, because you can see my maximum revenue, my cost, and of course you can see my break-even points here. And then even my break-even points match up on my profit, but then compare it to my maximum profit.